Hello everyone. My name is Have a good day. My name is Ankit Kumar and I'm a research scholar at Institute of Physics, Bhubaneswar, India. So I have presented my poster here on the topic of warm dense matter and cooling of supernova remnants, as you can see in the PDF on your screen. So the motivation of the work here is that using the relativistic mean field formalism, we have implied the temperature in the energy density or in the equation of state of a nuclear matter and see and study the effects of temperature on the properties of the nuclear matter and the neutron star. As you can see, the as all of us know that the neutron star are the one of the best laboratory to test our dense matter theory, which has a uh, very high dense matter in the core, up to 42, up to for 8 to 40 times of the and have mass up to 8 to 40 times of the sun. So we study the effects just after the, as you know that just after the supernova explosion, a newly born proton neutron star is thermally excited. Means it has some temperature and it cools down after so many years. After so many years, it cools down to a stable to a stable neutron star, which we call neutron star. So we also study how this newly born proton neutron star is cooled down through direct Urka process. These are the two main objectives of this work. Means to study the nuclear and thermal properties of the neutron star and to study the neutrino emissivity through direct Urka process. We have used there are so many parameter sets available for the relativistic mean field formalism. So we basically used three parameter sets for our work. NL3, which is familiar to everyone, and the IUFSU, and our recently developed parameter set G3. Using these three parameter sets, we study the incompressibility, symmetry, energy, slope parameter, and transition temperature of the symmetric nuclear matter, and also study the effect of temperature on the mass radius profile of the neutron star. So this is the temperature. This is the energy density expression on your screen for the temperature dependent RF model, where this F alpha nu T and F bar alpha nu T are the thermal distribution function of the particle and antiparticle, and these other terms are related to the meson fields, means sigma meson, omega meson, delta meson, etc. So using this energy density expression, we calculate the equation of state of the nuclear matter, and we see that how the temperature affects the stability of the symmetric nuclear matter. As you see in the figure 1, upper portion of the figure 1 shows that as we increase the temperature, so the binding energy of the binding energy per nucleon goes on decreasing. Means the system becomes less and less bind as we increase the temperature. And this procedure follow for this trend follow for all the three parameter sets which we assumed in our work. Also, the lower portion of the figure 1 shows the variation of pressure with temperature, and using this uh, uh, pressure using this variation of pressure with temperature, we can actually calculate the transition temperature, means liquid gas transition temperature in the nucleon matter system. And we find that the transition temperature is somewhere around For NL3, G3 and IFC parameter sets, as you can see in the upper portion of the figure 1, T is equal to 14.60 is the transition temperature for NL3 and 15.37 for G3 and 14.5 for FSC. We also study other properties like symmetry energy and effect of temperature on symmetry energy, incompressibility, and other thermal properties of the neutron star, which you can see in our recently published paper, this third reference from where we have to cover. And the figure 2 actually depicts the neutrino emissivity through direct Urka process in a neutron star. And it tells us, the figure 2 tells us that actually before going to figure 2, I will like to explain the figure 3. Figure 3 is the mass radius profile of the neutron star for all the three parameter sets. As we can see that the NL3 being the stiff equation of state gives the highest mass for the neutron star, and G3 and FSU gives slightly lower in comparison to NL3. So we can say that NL3 predicts the high massive neutron star, and G3 and IFSU equation of state predicts slightly lighter neutron star. And based on this fact, if we go to the figure right portion of the figure 2, means the neutrino emissivity, we can see that the neutrino emissivity for massive neutron star, means for NL3 parameter cell, is lower in comparison to G3 and IFSU. So we can say that on this basis we can say that the massive neutron star cools down through neutrino emissivity more slowly in comparison to the lighter neutron star. Means if a supernova means the bigger portion of the supernova remnants cools down slowly through direct Urka process in comparison to the smaller piece of the supernova remnants. These are the few observations which we can make on the basis of this work. And for more detailed explanation and for more detailed effects of temperature on the properties of the neutron star, you can go to the reference 3 and study all these effects or read all these effects. And in case of any question, doubts, or suggestion, feel free to contact me at my email ankit.k@iotb.is. Thank you.